In this exercise, we're going to develop a rational approximation to the exponential using Taylor expansion. So what we want is to determine constants a, b, c, and d, so that this rational function here is an approximation to the exponential in such a way that the difference divided by x4 is goes to 0 when x goes to 0. Well, there are many ways of doing this, but perhaps the easiest way is to just multiply, well, take the exponential, the expansion of the exponential up to fourth order, of course, as 1 plus x squared divided by 2, q divided by 6 plus x4 divided by 24 plus o x4 when x goes to 0, right? So we take this, and what we're going to do is we're going to multiply this whole equation by the denominator here. So we've got this expansion, right? So we have here this, the whole expansion, this one, and we multiply it by the denominator of this fraction, 1 plus cx plus dx squared. And then that is equal to the numerator, of course, 1 plus ax plus bx squared, plus, and then I have to multiply x4 times the denominator. But if you do that, let's see, we get here 1 plus ax plus dx squared. We got ox4 plus ox5 plus ox6. No, because constants is irrelevant, and when you multiply x squared by x4, you get ox6. But of course, these are ox4, so actually this is just ox4. So this is what we get here, okay? Right, so now we have to perform this multiplication, okay? And we're going to do it in powers. So let's multiply the 0th power, so the 1 by the 1, so you get 1 here, right? Then for the power of x, we get x times 1, which is 1, and then 1 times cs, which is c. So we have 1 plus c, right? Then we have the second power, x squared, right? And it multiplies, when you obtain x squared when you multiply this and this. So this is 1/2 here, plus this times this, which is c, plus, and then 1 times dx squared, so you get d. Then you get x cubed, right? X cubed is something that you get when you multiply this by 1, so you get 1/6 from here, and this by this, so it's c/2. Then you multiply this by that as d, and that's it, because there's no other multiplication that gives you x cubed, because there's no x cubed here, right? Okay, and then x4, you get it when you multiply, this is by the way x4, when you multiply x4 over 24 times 1, so you get the first factor is 1 over 24 plus, then you get this times this is c over 6, right? And then you get this times this d over 2. All right, and no more, because then there's no other multiplication that produces x4. This by that gives you x cubed, which is already counted here. So there's no more, because there are no more powers here. And finally, we have to multiply this by that, and as we have seen here, we just get ox4. All right. So this is the left-hand side, and the right-hand side is equal to 1 plus ax plus bx squared. So from this, well, of course, plus ox4. If these two expressions have to be the same, well, 1 and 1 cancel, right? Then the power of x must be the same, the power of x squared must be the same, and the powers of x cubed and x4 must be 0, because they are not here, right? So here you get, from the first one you get 1 plus c is equal to a, right? The second one gives you 1/2 plus c plus d is equal to b, right? This one here. And the third one gives you 1/6 plus c/2 plus d is equal to 0. And the last one gives you 1/24 plus c/6 plus d/2 is equal to 0. So we have here a system of 1, 2, 3, 4 equations and a, b, c, and d, so 4 unknowns. So it's a linear system, 4 equations, 4 unknowns. So we can just solve it, right? And the solution gives the following result. The solution is d is equal to 1/2, 1/12. Well, actually, you can solve these two first because these are two equations in C and D, and you get this and this as a solution, right? You can check it, just plug it in here, right? And then once you get these two, then getting A and B it's just a matter of substituting in these equations, and then you get A equal to 1/2 and B equal to 1/12. So it turns out that the rational approximation we're looking for looks like this. Is 1 plus x/2 plus x squared divided by 12 over 1 minus x/2 plus x squared divided by 12 plus x4 when x goes to 0. Okay, these kind of approximations, these rational approximations, are called in the literature Padès approximations. And turn out to be more useful to evaluate numerically the function you are approximating than simply the Taylor expansion. So these are preferred in numerical calculations to just an ordinary Taylor expansion in a polynomial.